So we want to find the radius and height required to maximize the volume of a cylinder that's open at one end, given it has a radius of r, a height of h, and a surface area of 8 centimeters squared. So we have our cylinder here, and let's say the top is open but the bottom's not, so the bottom's part of our thing, and we got a radius and we got to find the height that'll be necessary to do this. Well, then first off, we're trying to optimize volume, and volume of a cylinder is pi r squared h. Now we need to make a constraint equation based on the surface area. Now for a cylinder, the surface area, let's talk about the bottom first. It's just a circle, so that's pi r squared h. Takes care of the area of the bottom of this thing. It'd be 2 pi r squared h if it was closed on top too. Now the next thing is, if you imagine unraveling that cylinder, its side is just a long rectangle, and the length of that rectangle is basically that part right there. It's the circumference of the circle, so 2 pi r, and then this side is the same as this side, so h. So 2 pi r h finishes off our surface area. So we need to solve, there shouldn't be an h in here, excuse me, misspoke, we're just looking at area of a circle. What we're going to do now is solve this guy for h and plug it into this h here. This is equal to 8. So solving this for h, we have h equals 8 minus pi r squared all over 2 pi r. That is going to get plugged in for this h to get volume in terms of one variable. So volume equals pi r squared times 8 minus pi r squared over 2 pi r. Now we'll cancel anything to make this a little simpler. We can cancel out those pi's there, and we can cancel out one of the r's. And I like pulling the 1/2 out and writing it out front, but I like distributing the r, so we don't have to use product rule. So we have 8r minus pi r cubed. Now there's the function we need to optimize. We're going to do so by finding the derivative. So v prime equals 1/2. The derivative is 8 minus 3 pi r squared, just doing the derivative piece by piece. We set this to 0 and we solve for our critical point. Well, that's setting this to 0. Where is that going to happen? Where 8 equals 3 pi r squared. So we need to solve this for r squared by dividing by 3 pi. Divide by 3 pi, and then square root. Now we do not need to account for the positive and negative, because the only positive makes sense in this context. Now if we want to verify that this r value gives a maximum, we can look at the second derivative, which is 1/2 times negative 6 pi r, and notice at any positive r value the second derivative will be negative, which means concave down, which means our critical point sits at a max. Now we got to go back and find the h, which is going to come from plugging in this for our r's. So we have 8 minus pi times 8 over 3 pi squared over 2 pi times square root of 8 over 3 pi. Now the interesting thing about this is when you work this all out and simplify, you're actually going to get square root of 8 over 3 pi. So the height and the radius are the same. Height equals radius equals square root of 8 over 3 pi centimeters.